Assalamu alaikum warahmatullah. Let us continue with an example on the projection on one-dimensional subspace. So let's consider this line. Okay, this line. So there's a few things that we should notice here. First thing, that it's this line belongs to R3, right? Why? Because it has 3 elements, right? And it is a subspace because this line contains or runs through the origin point. If it does not contain the origin, we cannot call it a subspace, remember? So a subspace must contain the origin, the O0 vector. Okay, fine. So we, as we said before, so we can also write here that the subspace that we're talking about, call it again U, is actually what? The span of B. Okay, mathematically this means that so let's go upwards. Okay, so this means what? Let's say that a vector x belongs to U. When does it belong to U? When it satisfies x equals lambda times b, where lambda actually is what? It's a scalar, belongs to R, right? Okay, so here so the first thing that we want to do here is to find the projection matrix, which can be found by using equation 2.33, which is what? BB transpose, the outer product divided by the inner product. The inner product will give us what? A constant, and the outer product, this thing, will give us the matrix. 9 is the norm squared, right? Remember that this B transpose B is actually the norm squared. Okay, that's good. So it's a very simple example here, right? So let's say that we want to project the vector x. Let's say that we have another vector here. Let's call it x, right? So we have the vector x equals what? Say 1, 0, 1, right? And we want to find the projection of x into the subspace U. So we want to find this, right? Let's write it here. We want to find pi of U of x. How to do this? Simply say, okay, we use the projection matrix and we multiply by x. So what we have here is this thing, right? 1 over 9 or 1, 2, 2, 2, 4, 4, 2. This is a 4. Let's write it. This is a 4 again. Right, and we have this is a 2, 4, 4. Multiplied by what? 1, 0, 1. Okay. This will simply equal, let's leave the constant outside, so 1 over 9. This is a 9. And we have a vector, right? So what we have here is that the first element is 1 by 1, 2 by 0, plus 2 by 1, which is, we have 3. Okay. The second is we have 2 plus 4 is 6, and the same thing, yes, we have this. So this is the projection of x onto the subspace U. Very simple. Okay. Now let's consider a more useful and general extension, which is we have a subspace that is multidimensional, not only single dimensional. So the subspace U is spanned by the basis vectors from B1 to B sub n. Okay, so we use the same logic, right? So we say, okay, since that vector lives in U, belongs to U, it must be spanned by the basis vectors, and we can write it in a matrix format, right? Okay, so we want to find lambda. Here lambda, guys, lambda is what? Lambda is a vector now, because it has multiple components. Okay, what are its components? Lambda 1, lambda 2, until we reach lambda n, right? Because we have n components, meaning that the subspace, okay, U here is m-dimensional vector in a sense. Okay, so we need to find those unknowns, m unknowns. How we can find them? Using the orthogonality property. We say, okay, the projection of x is perpendicular to the complement of x. Okay, how we do that? Okay, let's say, okay, how do we get this thing, right? We say, okay, find the projection of x. Sorry, let's do this, right? So okay, we consider the projection of x onto U, right? We say that the inner product of the projection onto U is perpendicular to the error or its complement, right? As we did before, and this inner product equals 0. Okay. As we did earlier, we use the bilinear property to say that, okay, we have what? Pi of U multiplied by, and using the dot product, this should be what? Transpose. Okay. And this the pi transpose. Remember, pi is a vector. It is a projection, and so it is a vector. Okay, U now if we substitute this right here instead of this, right, we get this equation, which is 2.35, right? Now we have this equation. The b's are known, or the matrix B is known, which is the set of basis vectors. Lambda is the only unknown here. We solve it simply by using our linear algebra information, right? So we find the inverse and multiply it by the inverse. Okay. Remember, lambda is the coordinates. It's the vector of the unknowns. It's not actually the vector. The vector needs to be multiplied by x, which is the projection. So the projection is this whole thing, and we can deduce the projection matrix from this, right? So this is the x, and this is the projection s. So let's put it in this way, right? So this is the projection matrix. This is our vector, right? And all this is the projection matrix, pi. Okay, so we can use those formulas, right? 2.36, 2.37, 2.38 to find the coordinate, the projection, and the projection matrix. So let's take an example, right? So we have this vector that we want to project onto the subspace U that belongs to the vector space R3. The subspace, or the vector space, subspace, of course, U is spanned by those two vectors, right? So what is the dimension of U? So what is the dimension of U? The vector space U, it's 2, which is the number of the basis vectors. Okay, nonetheless, X here, of course, it belongs to R3, of course, because it has 3 components, and its projection belongs to U and R3, of course. Why? Because U also belongs to R3. Okay. Now, what you want to find is here, of course, you want to find the projection, right? You want to find the projection matrix, okay? And we want to find the same thing. We want to repeat part 1, which is finding the projection. What is the projection? This means that I want to find pi onto U of x pi, which is a vector. We want to find it in 2 ways. The, let's say, conventional method and using the projection matrix. The last part of the question is very important. We need to find the distance between x and U, which is the orthogonal distance, the perpendicular distance, and usually we refer to it as the error between the projection and the vector itself, right? Okay, so the first thing we do is we construct the basis matrix, right? And then if you want to find the projection, right, it's very simple. We use this equation, right, equation 2.37, right? We need to find this expression, B times B transpose B inverse times B transpose, right? So there's a transpose here. Okay, so we do it in a gradual manner. So if we first find B transpose B, right, which is this, and we find this B transpose X, and then we find lambda, which is B transpose B inverse. So we find the inverse of this, and we multiply it by the vector, and we get this vector. Remember, those are lambdas. What we do is now we multiply lambda by the basis, and this is the projection of x onto U. Right? Now we can find it in a different manner. We find the projection matrix, and then we multiply it by the vector x. So we have 2 ways, right? So here we just we found the projection matrix directly, and we multiply it by x, and we get the same vector. It should be the same vector, right? It is the same vector. So this and this, they are the same. Okay. Now what is the distance between x and U? When we say the distance, we mean the norm. Which norm? The L2 norm. Okay, the L2 norm. So we find this, this is pi, right? This is the original vector x. We take the difference between them, and then we find the norm. So what we have here actually is like this, right? So what we have here is 5 minus 6 is minus 1. This is 2, and this is minus 1, right? The L2 norm, this means that we have minus 1 squared plus 2 squared plus minus 1 squared equals square root of 6. Square root of 6. Okay. Now moving to the last part. Okay. So let's write it down. I think I moved this thing to here. Let's set that square root of 6. Okay, now for the last part here we have a projection into affine subspaces. What do you mean by affine subspaces? It is a subspace that is shifted by some vector, right? So if U is a subspace, an affine subspace is the vector space shifted by some vector, right? How we do it if we want to project on affine subspaces? We project on the original subspace, then we shift it. So the thing is that we let's say translate the vector x into the subspace U, do the projection, and then we translate it back. It's like this, right? So here we want to project x into L. What we do is that both of them, x and L, we subtract them or we shift them down, so L here contains the all zero vector. So this L is not what? A subspace. Why? Because it does not contain the all zero vector. So we can do the projection this way. So what we do is that we convert L into subspace by translating back into in a manner that contains the all zero vector. Sorry. Okay. We do the projection as we did before, and then we translate it back. Right. Now, after we've found the projection, now we translate it back into its original state. Okay. Thank you.